Almost everything you know about the cosmos has been discovered with some kind of light, gathered with telescopes. Sometimes those telescopes use light your eye cannot see, but it is light nonetheless. Recently, astronomers have started using particles like cosmic rays, particles from space, to do astronomy. We have also built vast arrays of detectors beneath the Antarctic ice to detect another kind of particle called a neutrino, trying to understand the distant universe. But the cosmos is full of things that don't emit light or particles at all, or if they do, only barely so, making them virtually undetectable from Earth. We see black holes by virtue of their influence on other things. We know about neutron stars and magnetars only by virtue of the few that are close to the Earth. Is there some way to see these objects better? Shortly after the introduction of general relativity, Einstein discovered a way: gravitational waves. If gravity is the curvature of space-time caused by the presence of mass, then the motion of mass should cause disturbances in the curvature that move, propagate, from one place to another in the cosmos. What do these gravitational waves, these ripples in curvature, do? Imagine two small masses in space-time. If a gravitational wave passes by, the curvature between the masses changes. Sometimes the spacetime is stretched, and sometimes it is compressed. The end result is that the gravitational waves change the distance between the small masses. How much does the distance change? Imagine two small test cubes only 1 meter apart. Then, a typical gravitational wave from the cosmos might change the distance between them by 10 to the minus 22 meters. That is a very tiny number. It was so tiny that Einstein thought we would never be able to detect these waves. But you and I live in the future. We have lasers and supercomputers and GPS satellites. We can contemplate what Einstein once thought was impossible. Our best hope is in detecting compact binaries formed from the skeletons of dead stars, white dwarfs, neutron stars, or black holes. When the members of the binary are far apart, they live happily in a regular Newtonian orbit. But over time, they fall closer together, and as they do, they emit gravitational waves. Those gravitational waves accelerate the falling together. We call this the in-spiral. Eventually, the dead stars get so close together, they merge in a titanic coalescence, which also emits gravitational waves. We call this the merger, and it leaves behind something new. Encoded in all these gravitational waves is a trove of information about the dead stars that emitted them. Far across the cosmos, those waves eventually wash across the Earth, whispers of the titanic struggle that created them, if we're patient enough to hear the tale.